My name is Cheyenne Scott, and this is our QEP project, and we did it on Chapter 6, Sections 6.1 to 6.3.
Hi, I'm Talisha Williams, and I'm doing 6.1 Properties of Gas. First, we have the kinetic molar theory. A gas consists of small particles that move rapidly in straight lines, have essentially no attractive for repulsive forces, are very far apart, have very small volumes compared to the volume in the container they occupy. They have kinetic energies that increase with an increase in temperature. We have pressure, the force that exerted by a gas against the walls of a container. Then we have volume, the space occupied by a gas. Temperature, the factor that determines kinetic energy and rate of motion of gas particles. And amount, the quality of gas present in a container.
Hi, my name is Kirsten, and I will be explaining Chapter 6.2, Gas Pressure. Gas pressure is a force acting on a specific area. Pressure P equals force over area. Pressure has units of ATM, mmHg, torr, pound over inches squared, or kilopascal. 1 ATM equals 760 mmHg. 1 ATM equals 760 torr. 1 ATM equals 14.7 pounds over inches squared. 1 ATM equals 101,325 pascals. 1 ATM equals 101.325. Here's an example of how to convert mmHg into ATM. What is 475 mmHg expressed in ATM? You take 475 and you times it by 1 ATM, and then you divide it by 760, and it gives you 0.625 ATM.
Hi, I'm Ellington Hayes, and I will be explaining 6.3 Boyle's Law. Boyle's Law states that the pressure of a gas is inversely related to its volume when T, the temperature, and N, the amount, are constant. It also states that the product P, pressure, times volume is constant when the temperature and moles are held at constant. It also states that if the volume decreases, the pressure increases. Pressure 1, volume 1 equals pressure 2 times volume 2.
Once again, I'm Cheyenne Scott, and I will be doing an example for Boyle's Law. The example says, a gas occupies a volume of 120 milliliters at 700 millimeters of mercury. What volume does it occupy at a pressure of 150 millimeters of mercury? It gave us volume 1 and pressure 1, and we're looking for the volume 2 for the pressure 2. Okay, and the formula states that P1 V1 equals to P2 V2. And since we're looking for volume 2, we're going to divide both of these by P2, marking these out because we're dividing, and we're going to be left with V2 equals to V1 times P1 over P2. So when we actually write this out, put it in this formula, it's going to be 120 millimeters times 700 millimeters of mercury over 150 millimeters of mercury again. And then our answer is going to end up being in milliliters. So our final answer is going to be, once you times all of this times this, and then divide these two answers, we're going to be left with 560 milliliters equal to V2. So, okay, we're going to do one more problem for Boyle's Law so that you get a better understanding with what the actual formula is asking you to do. So the next example says, a 2.50 liter sample of helium gas has a pressure of 500 millimeters of mercury. What will the new pressure be in millimeters of mercury if the volume is reduced to 1.00 liters? So they gave us pressure 1 and volume 1, and we got to find pressure 2 because they gave us the volume 2. So, and this is the formula. Once again, this is the formula. P1 times P1 V1 equals to P2 V2. So since we're looking for P2, Then we're going to divide both of these, and we're going to divide it by volume 2 and mark both of these out so that you're only left with P2 equal to P1 times V1 over V2. So when you actually write this formula out, you're going to plug in 500 millimeters of Mg times 2.50 liters over 1.00 liters. And your final answer is going to be, once you times all of this out, your final answer is going to be 1,250 liters left in your final answer.
During this presentation, we went over 6.1, properties of gas, kinetic molecular theory of gas, 6.2, gas pressure. We talked about pressure, volume, temperature, and amount. And 6.3, Boyle's law. Pressure 1 times volume 1 equals pressure 2 times volume 2, and how they are inversely related.